one of the consequences of presence of domains in ferroelectric materials is hysteresis. I'm sorry about this. Is the presence of hysteresis loop and switching. So let's imagine that we have a piezoelectric crystal or ceramic, and after we sintered it, and we at the beginning we will have domains in general, a very complex domain structure, as you have seen for ceramic materials. And then we apply electrical field, and by application of electric field we will get polarization. Hysteresis loop will follow the following trace. So by applying field from 0 to positive and then going back, so field, if strong enough, will start reorienting domains along those crystallographic directions that are allowed by the crystal symmetry. Remember, in a tetragonal material, domains can only, polarization strain can only develop along 0, 0, 1 and perpendicular to perpendicular directions under 90 degrees. They cannot develop under other directions. That's not allowed by the symmetry of tetragonal sample. So we will orient domains as much as it is possible. In the case of a single crystal, we can orient them and in such way that we get a single domain crystal, while in ceramics it will never be possible because of the random orientation of grains to align all domains in the same direction. This point here is called maximal polarization, and if we go down, make projection of that to zero field, we get a point which is called spontaneous polarization. Okay, now when we go down with the field, some of the domains will go back to their line with the field. So at the zero field in general, we will not reach the same point that we will not reach the spontaneous polarization. The slope here is simply the fact that by applying electrical field, we will be inducing, in addition to spontaneous polarization, also some induced polarization. That is why we are making this projection. And then if we start going with the field down, some of the domains will be oriented against the field at some point which is called coercive field. Approximately half of the domains will be oriented along field direction and half against, so the polarization will be equal to 0. That's called coercive field. And then we will reach the same point as on a positive field in the negative field. And then when we further reduce field down to 0, we will go through the point of negative remnant polarization and come here to 0. So if we had an unpoled ceramic, the field cycle, the polarization as a function of the field would look like this. And then if we apply field again, we will start with this point, and then we would do that. So from the shape of the hysteresis loop, you can know whether the starting point of your sample was whether the sample was poled or not, and so on. So hysteresis loop is a consequence of presence of domains the fact that different polarization states are all equilibrium states, all stable states, and this switching is also a characteristic of ferroelectric materials. If you have a pyroelectric material where you have polarization but cannot be switched, you would not have this hysteresis. So if you are looking for to detect whether a material is ferroelectric, we usually the sign of that is presence of hysteresis. One of the signs of ferroelectricity is hysteresis. I will discuss that a little bit later. So with ceramics, we have the following case. Let's say that we have a ceramic that is ferroelectric. We sinter ceramic at some high temperature. These temperatures are almost always higher than Curie temperature, so material is in a cubic phase. There are some exceptions. For example, in a bismuth ferrite, we usually do sintering below Curie temperature. So after sintering, and at temperatures that are higher than Curie temperature, we will have a cubic grains, no polarization. And then as we cool material and we go to TC, the polarization will develop and domain walls will be formed in the material, so that because of the random arrangement of the grains and presence of domains, the net polarization is equal to 0. So the polarization is equal to 0. However, if you apply electric field, and that electric field can be applied either below TC or above TC, and then sample is cooled to room temperature, we can align polarization in grains along one of the polar directions. Since grains are oriented differently, not all of them. So for this one, C-axis is here, C-axis is here, and so on. We will usually not have that any of the grains in a ceramic are single domain. And that's because there will be some strain in every grain due to surrounding material, which doesn't have the same orientation. And while we can get rid of most of the 180-degree domains, some 90-degree domains almost always remain in a sample. Now, there are materials that are uniaxial ferroelectric, such as lithium niobate, in which you have only 180-degree domains, and there it might be possible. I actually don't know whether one can have a ceramic without any domains in a lithium niobate ceramics. What kind of domain walls are possible in ferroelectric materials can be determined from the symmetry of the paraelectric phase. That's phase, non-ferroelectric phase above TC. We call it paraelectric phase. And from the symmetry of that phase, you can actually tell what by the symmetry of the material, what kind of domain walls you might have. That doesn't mean that all those states will develop, but those are possible states by the symmetry. And I have given previously, I'm not going to go back to that, but there are two papers by Aizu in which he derives for all crystal symmetries what are the possible domain states that one can get. So you can find those two references on one of the previous slides. So if you look at a cube here, we are looking at symmetry, different symmetry elements, and we see that we have these. So these are along the crystallographic axis. That would give us a tetragonal phase. For example, if we start with M3M phase, cubic M3 bar M phase, we can get tetragonal phase 4mm with 6 states, and that will give you 180 and 90 degree domain walls. Then you can also look at these elements along side diagonals of the cube. Polarization can develop along those, and that will give you orthorhombic MM2 structure with 12 possible states. And the domain walls can be 180, 60, 120, and 90. And then you can look symmetry with respect to diagonal of the cube. And that can give you rhomboidal 3M phase with 8 possible domain states. So here we have 12, 6 along sides, and plus minus because of 180 degrees. That gives you a total of 12. And here we have 4 diagonals, body diagonals, and then plus and minus 180. You can get 71, 109, and 180 domain walls. It is possible that M3M also gives you monoclinic structures, which have been discovered in many of these more complex ferroelectric materials, not in a barium titanate. For example, lead titanate, barium titanate, both have a M3M structure, but this one gives you only M3M cubic structure, but this one gives you only 4mm ferroelectric phase, while this one gives these 3 tetragonal, rhomboidal, and orthorhombic phase. Domain walls are intimately connected to what is called ferroic materials, and I just want to give you a word on that because it's a very popular topic now. People are looking for a multiferroic materials. Those would be materials that are at the same time ferroelectric and ferromagnetic. And what would that mean? That would mean that you can affect magnetization by electric field or polarization by magnetic field. And that would be really interesting from the point of view of devices. Such materials have been discovered, but they are usually multiferroic at very low temperatures. Some of them are multiferroic at room temperature, such as bismuth ferrite, but it is not ferromagnetic, but anti-ferromagnetic, and so that's not so useful. So basically any material which develops domains, either electric and electric domains, or magnetic domains, or elastic domains, is called a ferroic material. So, for example, barium titanate is a multiferroic material. It is ferroelectric and also ferroelastic because it has this strain that develops at a phase transition. However, its 90-degree domains, which are ferroelastic domains, are also at the same time ferroelectric. So it is a ferroelectric, ferroelastic material, but it has purely ferroelectric domains and ferroelectric, ferroelastic. It doesn't have purely ferroelastic domains. Material that is ferroelastic without having polarization is, for example, zirconium dioxide. You can learn about this from Newnham's book. There is a whole chapter on ferroic materials, and basically the treatment is the following. You have a cubic material Okay, there is no polarization. And as you go through the phase transition through TC, you develop these two. So polarization is 0 here. Then we go into ferroelectric phase. We have two states of polarization, which are equivalent but different directions. Those two states have to differ somehow. And then when we apply external electric field, we are introducing a symmetry between these normally equivalent states. They are no longer equivalent. One of them is preferred with respect to the other. Okay, so this state is preferred to this one. It has a lower energy, and the difference in the energy between these two states is a driving force for moving domain wall. Okay, so if you had a two domain walls, one of them polarization looking down, one looking up, if you apply electric field in this direction, this domain here we switch that. We say that this domain polarization in this domain will switch, and we say that this domain wall will move to the right. And you can actually observe it in a microscope, how it moves. I have some films, but it was challenging to prepare it for this. So from these differences in states, in a polarization, strain, magnetization, and so on, is what defines under external fields, is what defines ferroic materials. And then you have, for example, ferrobi-elastic. This is a different in elastic coefficient. You have ferrobi-electric, ferrobi-magnetic, and then you have ferro, I think B electroelastic, where you have a difference in a piezoelectric constants between two different states, and so on. So you can read this about this in Unem's book. But there is energy reason why domain wall will move, which really is intuitively obvious. So let's see how this movement of the domain wall can affect piezoelectric response. This is what's of interest for us in this course. So again, this is a schematic reasoning. You will probably find some reason why this is not completely consistent, but try to follow the general idea. So let's say we have a crystal which gives us two domains, one which is going polarization going down, and one where polarization is going up. And we now apply electric field in this direction, which means that we are energetically preferring this orientation of polarization to this one. That means that this domain wall will move. So it will move on expense of this polarization. So we will get that now the positive domain is this, and the negative domain is this. Now let's see what's the difference between these two states. Well, the difference is this yellow part. Okay, that's the difference between this state and this state. These two give you in total zero polarization, but what you have gained in a polarization is this volume here. So the new part here and the difference of them, the effective polarization is positive polarization is this one. If we now apply field in the opposite direction, we will move this domain wall in this direction. So it will displace like this. Again, this part and this part cancel if you want, and it's this central part which remains as effective polarization in the material. But look what happens. In both cases, final polarization and the field have the same direction. Okay, nothing has changed. And you know what happens in a piezoelectric material. In a piezoelectric material, when we turn field upside down, sample goes from extension to contraction. And here, since the field is along polarization, it will, for example, expand it. And in this case, field is still in the same direction as net polarization and will also expand it. So application of the field in both cases expand crystal. That's not piezoelectric effect. So movement of this wall didn't change piezoelectric effect. Of course, if I apply additional AC field, that would be different. But considering just this field that we are applying, under which we are observing domain wall movement, we don't have contribution to piezoelectric effect. So displacement of 180-degree domain wall does not contribute to the piezoelectric effect. Okay? So piezoelectric effect requires this. When field changes direction, that response changes direction. What we have from 180-degree domain walls, and that for both directions of the field, we have the same, either positive or negative response. So from displacement of 180-degree domain walls, we don't have piezoelectricity. What is this? Well, if you remember previously when we were discussing higher order terms, this looks just like electrostriction. Okay. So it looks as though 180-degree displacement of 180-degree domain walls would in fact contribute to electrostrictive effect. Now let's see 90-degree domain walls. What happens there? Well, I'm exaggerating a little bit here the formation of the crystal. The two domains are never, and it comes geometrically, I'm not going to go into that, but you cannot have 80 exactly 90-degree angle between polarization two domains. You have seen, look at these pictures that I have given before for a high resolution, atomic resolution domains, and you will see that there is a small that angle is not exactly 90 degrees, but a little bit smaller, I think about half a degrees. And that's just to make possible continuity of the lattice. Now, I'm exaggerating here, but imagine that we have a crystal in which there is one domain wall. Now, when we apply electric field in this direction, this domain wall will move on expense of this one, and the crystal will change its dimension, its size by some factor delta L. If I apply field in this direction, then I will move this domain wall down by the same by the basically same amount, but it will be minus delta L with respect to this one. So I'm not drawing this nicely, something like this, where this is above this line and this is below this line. I think the actual drawing is better than what I can do with the pen. So while a normal piezoelectric response would give you something like this. Here you have that from displacement of 90-degree domain walls, we will get a response which extends crystal when field is one direction and which contracts crystal when field changes direction. That means that movement of 90-degree domain walls will actually contribute to the piezoelectric effect. And we can make this very general statement in ferroelectric domain walls will contribute to piezoelectricity, while purely ferroelectric domain walls, which are not also ferroelastic, will not contribute to the piezoelectric effect. So I will stop here and we will continue on the same topic